partitioning that we used on the Europa Clipper flight software. This is the flight software that runs on the main avionics computer. There's other flight software elements on the spacecraft or radio or devices or instruments, but we're talking about what's essentially the bus controller of the software, so the spacecraft bus. And you know, coming off of Mars Science Laboratory and Curiosity mission, there was a strategic objective within the division at JPL to sort of migrate to a improved flight hardware and software solution of A-Ring 653 was very much of interest, and a push towards that standard, and maybe even more so, but at the same time, the idea to improve the software that was developed for the Curiosity mission that was sort of already evolved from a few earlier missions, and to bring in, turn it more into a product line that could be deployed more easily, more rapidly, primarily focused at flagship style mission, but not restricted to it, right? And of course, so there's lots of reasons for this. Main ones I'll hit here, but go into much more info later on, is to reap some of the perceived benefits, reusability, obviously the big one, but also fault protection that you get through the A-Ring platform, structured design, and also V&V. So there's a lot of potential benefits with this approach, distributed development, and also strategically sort of seeing that as a stepping stone towards future platforms for flight software, in particular multi-core systems, much smaller distributed processing systems, and not really just not seeing JPL being able to compete and deploy this rapidly on new missions. So that was one of the main objectives of going down there. The approach here was, at JPL, we had previous attempts to sort of complete grand restart of how to do software, and those didn't always work out too well. So this approach was intentionally more of an evolutionary approach from the MSL code, both hardware and software, towards the A-Ring initiative. It started out funded by sort of internal research and development funding, but then also got picked up by the Europa Clipper mission as the way to build the sort of next flagship mission. It was probably about 7 years ago or so, and use this approach for the flight software, again, for the avionics. So perspective here, this is sort of very my specific viewpoint. You're going to get, you know, everybody on the team is going to have a much different viewpoint, and there's lots of them. So this is really from the perspective of the management. I'm sort of more on the programmatic side than the technical, I'll be honest about that. But the viewpoint of, for this project only too, because what you're going to take out of time and space is going to vary on what you're able to do and to what extent you're going to be able to deploy it. And you'll see some of the gaps of the benefits that you might get from time and space versus what we were able to reap from it, just because we weren't able to do everything, even as much funding as this mission had. So quick one slide primer on time and space. It's, you recall it, traditional sort of embedded software systems entail sort of interrupts happening all the time, perhaps, or event-driven tasks all mixed together sometimes. On MSL side, it was mostly priority preemptive, but there was also some rate scheduled going on, synchronized with the GNC area. So it was all mixed together, and it was competing for CPU and competing for sort of design resources and getting somewhat intertwined, sharing common memory. So there can be errors that do result in sort of unintended corruption and of one area for another, and certainly the prioritization, handling all the interrupts, we had a lot of them, was quite a challenge. And there was this goal towards stepping back to towards a more deterministic system. Time and space was seen as offering that, and as well as some of the other things you'll see coming up, right? So space partitioning is where software code is divided into a set of distinct partitions, such that each partition operates pretty much as its own virtual address space managed by the RTOS and using the CPU MMU. And it's pretty much isolated, almost as its own process, or the VxWorks RTP is sort of using that as an example. A component or partition accesses data within that's virtual address space, but can't access data outside it. The RTOS actually prevents that, unless there's some specific constructs for getting data across or sharing messages or sometimes a read-only shared memory construct. So you can obviously build these brick walls, but then you still have to get data across, so then you have to provide ways of getting that data across. An out-of-bounds memory address attempt is an error and will result in a response that is configurable, right? You can suspend that particular partition and keep the rest of the system going and things like that. So, but it will not propagate to the other partitions is the whole theory here. Time is sort of similar. The way we deployed it, time and space partitions are each the same partition, has both boundaries. And it's really from an execution perspective. So it only executes within its allotted time slice. And it can have multiple threads within that partition, but they can't step into another time partition. And it's sort of, again, like a mini system. You can have rate groups within there, priority preemptive within that partition. So you're sort of seeing a little bit more overhead there too, because now you might have a 16 hertz rate group in one partition, and then you do the same thing in the next one and the next one. So there can be overhead, and that was one of the concerns. But essentially, each partition is independent and guaranteed by the RTOS to be able to run no matter what's happening in one of the others. And there is quite a bit of variability that you can employ. You don't have to just time slice it into a set of bins and everybody runs at the same rate. You can have time slices shared, so you can control that in one sort of minor frame. This one runs in that time slice, and another minor frame, another partition runs. So there's lots of variability, and depending on the RTOS, there's a little bit more flexibility on what you do with background tasks too. So the next two slides, and actually the third slide, which is the challenges, are exactly the bullets that we had prepared before we started for some of the management. They were asking, well, some of the people weren't quite sure what you get out of this. Why would we approach this? So these are sort of unfiltered what they were. And what I tried to do with this talk is sort of show you, well, how did we meet those? Just looking back at hindsight, again, from my perspective, right? So mission safety, right? That's a big one. Oh, time and space protection. That's why you do it. So one partition can't step on another, and you've got safe execution. So faults in a particular partition do not stop other partitions from executing, lockup, or pretty much freezing in any way, right? Sorry, the font here is a little bit small. One partition will not prevent another partition from operating. So how did we do on that? It's a sort of yes and no. Yes, the system does that. That was one of the early objectives. Test it out. Fault here, keeps running over there. The problem is in real life, we were sort of running into is that on a spacecraft bus flight software, pretty much everything is critical, and you can't really keep running without your thermal system or your GNC partition, right? So, and it would take too much effort to sort of structure the application so that they gracefully losing sort of input I/O. So even though the I/O, that partition can die, but if the other partition isn't getting its data, well, there's a little bit of a problem. So that's not quite as perfect. We'll jump into that a little bit more. Safer mixing of multiple software criticality levels in a single flight computer. Yes, absolutely. It does that for you. You can do that. And there was a big focus on setting up. There was a ton of thinking about how to structure your partitions, obviously by cohesion and by what they're doing, but also by criticality levels. So thinking about it so that you can actually let them fail. And again, that's sort of, you can build components to be able to handle the criticality at different levels and stay suspended. We have an instrument partition, and in theory, it could die and the spacecraft would be safe, right? Again, we didn't do that just because, you'll hear this theme, it's sort of smaller steps, right? So this already was a pretty big jump for us. And so we didn't take advantage of everything. Assured access to time and memory for each partition. So absolutely we saw that. Even when we had overruns It didn't affect the other partitions until we actually chose to bring the system down and restart it. So you can see things running, and the system does absolutely provide this. Oops, I'm jumping ahead. All right, applications can be added or removed to the system. Oh, yeah, I remember seeing a little presentation with the iPhone, and here, look, you can just download this from the App Store and install it on your spacecraft, which is really tempting, and the architecture in theory supports that, but in practicality, that's just not reasonable, right? So you can't can let failed non-critical partitions stay down, but even that is a theory thing, because making the system robust enough to do that takes a lot of effort. So it seemed too ambitious to go anywhere near even the second bullet there under that, let alone the first one of adding stuff. There's so much work in creating these functions and years of development that just adding something onto the spacecraft later on in hindsight seems, pretty far away. But again, the architecture in theory would support that, the time and space, that is. Using a certified operating system, hey, there's ARINC. Again, with ARINC that came. We ended up not going down that path, really because the certified RTOSs are a lot more expensive. And I think I allude to it later. They also are more restrictive. And we're used to, if you need to on a spacecraft, you can go in there and patch something. And if you know what you're doing, it's sort of dangerous, but there's scenarios where that's saved the day. And sometimes you also want some flexibility with avionics, but mainly the cost. That was a big scale back. So we did just go to what I would call uncertified time and space. Highly structured interface components. These sort of overlap. You'll see some of these bullets are a little bit similar, and that's all right. So yeah, I think the common patterns for partitions made development easier, sort of cleaner in the end. We had a pattern on how they communicate across the partitions and the services that are traditional spacecraft services, the APIs they provided. The problem is, even though this is a check mark yes, because you're doing time and space, they're actually pretty complicated still. So there is a common pattern, but there is complexity built into trying to sort of get over these brick walls that you've created. So I'll sort of say it this way. Not everyone agrees that this point, and you could probably do this pretty effectively if you had a disciplined design and a development rule set. You wouldn't necessarily need time and space to do this, but the time and space does get you there too. Build different elements of the system separately. So distributed development. You might be working with a partner that perhaps has less rigorous development practices, and you're worried about them sort of corrupting other parts of the code with time and space. That is there's an opportunity there to say, here, you've got your own partition. You can do whatever you want in there. If you crash, we don't care. We're going to keep running. So we don't have that need on Clipper, but you might. In having that, it can be really good, and especially with partners, you can have different pieces shipped out and developed independently and tested independently. But that's the next page. We didn't do that on Clipper. We didn't have that need, but that was one of the strategic objectives of the division, and was seen as a plus for going to time and space. Proper partitioning should ease development of highly complex systems. I think that's a lot like the first one under development. It's sort of, the partitioning does structure things by switching to time and space. We didn't just switch to time and space, we switched to a less interrupt driven system, more polling architecture, and a lot, try to eliminate all the interrupts, and that together is sort of hard to deconvolve those, but it certainly led to a more understandable, when stuff is happening, what's happening. Still need to work on why sometimes, but it certainly did help. Okay, second set of benefits here. V&V. So you have limited communication mechanism between partition, and again, that should simplify your verification. You can build a partition and actually test it as a partition. We didn't do that. This was a big step, and we knew how to do V&V very well, and you sort of have to fall on what you know and get the job done, because you still have to deliver the spacecraft. And they did a lot of new things, especially with tooling and automated regression. But I sort of, maybe these sets go together, so I'll put them up together. You have to not just sort of decide to test it by partition. You actually have to build like a test harness that provides the ability to test out a partition, whatever API you create for that partition to execute in. You can actually completely, it's almost like a unit test, but for an entire partition, all the modules and functionality in there. But you have to be able to drive it as a partition and provided that API and let it sort of be executed and test that way. And again, we just didn't have the horsepower to get that far. This, I think it can be a big plus. We really saw it as, oh, that would be great, but we were just unable to get there in this project. We kept it requirement-based and traditionally functional-based, and maybe that's a good step, because you've got this new thing and you've got a system that you know how to do, so you're able to verify and validate that that system works the same, even though it's implemented differently, right? So we didn't reap that benefit, not yet, but that's still out there, and you'll see that where sort of this talk goes down the line is sort of, that doesn't mean you can't do that still going forward, right? Component testing has higher fidelity. Yes, again, it requires building a partition-focused test harness. Avoid or limit the need to rebuild and reevaluate the entire system if you're just changing, what did I have there before? Sorry. Is required or application. So the idea here is that on that last sub-bullet is, can you just isolate your retest to the partition that had changes only? Yes and no. So that's sort of both, right? Yes, you can, because you're much more confident that a change there isn't going to sort of wildly change something outside of its bounds. And when you have a finite amount of time before that delivery is needed, and you know your tests, you know your code changes are to that partition, that's where you're going to focus it, and you're going to sort of go on risk and accept the risk that it didn't corrupt things outside that partition. But it's still a system, and it needs to work as a system. So there's data going back and forth, and you can change what data goes across the partition boundary and actually change the system behavior. So we still have sort of a cross-cutting test that verifies everything, but you don't necessarily need to go down and test each partition within itself. I mean, optimally, yes, but in reality, this does let you take some shortcuts and accept the risk. So having that partition boundary does let you limit what you're going to test, even though in theory it can still, the communication goes across boundaries, so the error can go with it. Reusability. Oh, that's a little bit of a hot topic. I think within ourselves we did get a common app pattern, and we spent a lot of time, you'll see, developing the infrastructure and figuring out how to get it right. But then once we got into the Europa specific modules for the instruments or the bulk data storage system, sort of the application type features, I think it went a lot easier, and you could actually take the patterns from one partition, replicate it, and jump straight to the implementation on that. So yes, I think we reaped some of that even within the project. I'll talk a little bit, very little bit, Psyche and sample return rover. There is an intent to reuse it. Psyche did pick up a lot of our infrastructure and save a lot of time doing that, but it was an early version in the middle of development, so that came with its own lessons. They've had some problems because they had a launch slip, but the manager there says it's not at all attributed to time and space. So I don't get that out there. SRL, they're still sort of figuring out exactly what they want to do, and we'll see where that goes. But there is an intent to try to reuse some of this, but also bring in some of the very Mars-specific code as well. So that'll be interesting how that plays out. Abstraction layer should support increased processor portability. Yeah, we'll see how we're not dealing with that yet. But in theory, it should. There is an OS abstraction layer, and it should port. I'll get to it probably a little bit later as well, or not, but maybe. We did initially start out using some of the more OS provided features and then scaled back away from those because we didn't like the baggage that came with them and used more of the vanilla interfaces and built our own sort of machinery around that. So that should help the portability. Partition loading. So MSL took more than a day to get a new version up there. So with this partitioning, we actually can build completely independent components or partition set of files, and just if there's a change and it's isolated one, you just figure out which files those are, that the dynamically linked library that goes with that partition and the code, and you can ship that up independently. So that's a new thing. That's definitely going to be a lot quicker. Even the big partitions are still just a fraction of what the entire monolith would have been. Okay, challenges. Oh, safety. Isolating a fault to one partition doesn't help if you find that if that is a critical component, right? Yeah, so we knew that. Even though that's obvious, we already knew that before we even started that, yes, we're touting mission safety, but at the same time, pretty much everything's actually a critical component, and that turned out to be true. And it actually made many people sort of skeptical, because that's sort of the only part of the system they understood. And they're saying, well, if you're not doing that, why are you doing partition? Right? So it's fair. Well, we were sort of saying that that's something you get with partitioning, but we didn't really take advantage of it. So that's fair criticism. Resources. So potential CPU utilization issues. We were actually quite worried about this early on. We did some initial measurements, and we thought we'd be okay, but until you really implement the system, you don't know. And so it was a bit scary. And the complexity that came out of this and specifying there is overhead. It's tricky, but it's not unmanageable. Additional context switch overhead is there. It does add load. It was sort of coupled by the fact that we have very old processor. And you also have to deal with, JPL has some pretty strict margin requirements on computing resources, and it's really hard to figure out what that means with time and space partitioning. It's bad enough when you have one system and you have real time and non-real time, and you're trying to explain to people why your CPU goes up to 100% for little bits of time. Doing that with multiple partitions is even tougher, because you have to sort of decide how much overhead you need in each one of those. But it turned out to be not too bad. I talk about that a little bit more. Certainly memory usage was a big, now this mission came with 1 gigabyte, so we got like 4x memory more than we had anywhere before, so that wasn't a big issue for us, but if you have memory constraints, that could be. Development. Restricts development to provided interfaces. So again, this was with A-Rank 653. It wasn't a big problem for us because we scaled back from A-Rank and did move to custom functions, as I talked about, not sort of canned by the RTOS. So that wasn't a big issue for us. It did come with work, cost money, but we have them there if we need it. And there are some back doors that can be lifelines. So that wasn't. But again, it wasn't a big concern as we thought. There was concern about, are you going to use different schedules, and how's that going to sort of explode your V&V effort? That didn't turn out to be a problem because we didn't need multiple schedules. We actually kept, and Psyche did the same thing. We kept one base schedule and used that from initialization through all the modes. You could if you need to, but we didn't have to do that, so we didn't suffer that. And it seemed to work. Most of the time you got the GNC running, you're still uplinking and downlinking, so you've got all your functions pretty much operating most of the time anyway, so we didn't see the need. There was a time where we sort of considered it for initialization, where there's some of your file system management needs a lot of time to do things and such, but we didn't have to do that. And we told management early on this was going to take a full project to really understand, and that is absolutely true. The management changed, so they believe that. So you sort of have to, this is a learning, long process experience, and so no quick answers on any of this. And even this is, you can see from this presentation, there's a lot of, well, maybe next time we'll be able to add some more. So it's a long journey. All right, more hindsight. Wow, this took a lot more effort than we thought it was going to. We had a couple of cross-cutting services that actually needed to be reworked more than once. We sort of did it one way, it seemed like the right way. Oh, look, it's using way too much CPU. or it's just too much of a pain for the client modules. So yeah, it was a bigger learning curve. It took more time, much more time than we thought it would. And it's still not ideal. I think our message sharing is still too complex, and we'd like to redo it one more time. It's not just a flight software or avionics impact. It's actually changing how the system behaves, and some people weren't happy about that. They worked on previous missions. And they said, I want that. I want it that way. And one example is long latency. If you've got things in 1 Hertz rate groups and multiple partitions, by the time they get to each other, it can be a little while. So most of those weren't deal breakers. There were a few like that, and there were some grumbles from the systems team, but it really isn't just, and also the product line, by the way, too. It's not just flight software. You got to get your avionics system engineers on board and try to make that as a system choice. Our previous RTOS had some simulation limitations that actually led us to switch to a new RTOS, so that it was not just time and space partition, not just product line. It was a new RTOS at the same time. So talk about killing yourself. That was a lot of work. We had pretty much been on that previous RTOS for years and knew it very well, and it was a completely new ball game with this one. Different approach on tools and how they run things. So it actually was quite a bit of effort. A-Rank 653 involves very expensive and restricted solutions. So we did an extensive trade study. It led us to a different vendor. Let's see, last bullet here. With deep space spacecraft, there's very little that isn't critical. Yes, I already mentioned that. So partition restart. The idea of having one partition fail and having it restarted in real time without affecting anybody else sounds great. We'd love to do that, but we abandoned that as being too ambitious again. We were already having enough trouble getting the basic services working well and effectively. So you can see this is a challenge. This is not a faint of heart approach to jump to this. Some other lessons. Oh boy, I'm really glad we were able to hire a couple of experienced time and space experienced engineers, and it really made a big difference. They came with experience and lessons, and were invaluable in helping us sort of navigate this journey. I talked a little bit about CPU usage. It wasn't a high risk concern, but it was a high risk concern, but it really didn't become a major issue. I already talked a little bit about just how to report margins and in terms of, because you have multiple components running at the same time. But again, a lot of that is we're trying to do all these things, but still with a really slow processor, relatively speaking. So that's probably was the most challenging part of it, but we do think it's an investment that as the processor base increase, you can do a lot more with. We were hitting overruns pretty early and initially fairly often. I'm sort of trying to say, is this good or bad? I think it certainly draws out errors sooner, right? With the old system, you don't hit those overruns till you got most of the CPU loaded up and your application almost finished. With this way, you sort of had your time slots, and as soon as you finished one set of functionality and it's all implemented, you can stress it out, and you're seeing, oh, okay, that's hitting its limits, and there's I guess what I would call tuning. So the changes to the partition schedule were actually fairly easy to make, and actually so was moving modules from one partition to the other. So sometimes we initially thought, oh, the remote engineering unit, we'd keep that separately. We merged it in with the I/O, and the sequencing engine, oh, we can bring that in together with command handling and uplink, and so moving those together wasn't a big deal, and didn't it took a day or so to change the machinery and get it reintegrated, and for the most part it worked. So tuning also, just deciding, move a little CPU from here to here. Oh, look, this guy has lots of headroom, and he's very stable. We're never going to run into this case where we use up all the CPU. We can steal some of that. So that turned out to be pretty easy. We're still tuning. There actually was, it's easy to forget now towards the end, but there was early on a lot of times we implemented something and realized it took too much CPU. and the memory access on this mission's a little slower, things like that. So it's hard to deconvolve those again. But again, it did not, that wasn't a major driver. I do have this little thing on the bottom here, just because it's sort of cool and maybe people are interested. COVID happened right in the middle of us developing, and I had really good metrics for each build and exactly how we were progressing on earned value. And this is just the development, not the V&V side, but it was sort of showing right I was watching the data week by week after we got the stay-at-home order, and we already had a few remote developers, so we sort of had the communications machinery going, and we had good data on productivity, and it actually went up during COVID initially, surprisingly. So management was very worried about what the effect of it was, and you could sort of see the slopes with these red lines. It went up for about 6 weeks, and then it settled right back down to where it was. I think maybe that was nobody was taking vacation or time off. Maybe it was just they were captive audience. So that's an interesting data point I threw in there. All right. How am I doing on time? I'm past. Okay. Advice to others. Key considerations. You sort of, can your hardware system accept the latency in interrupt handling, response times, buffers large enough? Will you benefit from the advantages? And does your org want to, and can it adapt to a mindset, right? Can you accept the initial hit on learning, converting, tool, licensing? It's a long-term buy-in. It's not a simple decision. And since I'm off time, maybe I will skip past this last chart. Again, so it's a long journey is the main conclusion. I'll leave this up, then you can read it if you want during questions.
Well,
or do we not have time?
We'll at least take one question from Slack. So I've got one here.